In the last two lectures, we have discussed the two fundamental aspects of casting like heat transfer and segregation, and in this lecture I will cover morphology of solidification structure, and not only that, along with it I will also discuss the ingot casting. I will briefly discuss the ingot casting because ingot casting nowadays is not used too much, and only some forging purpose some ingots are cast. Usually for flat products ingots are not cast today. It is flat products are made mostly by the continuous casting. So the concept that will be covered, that is, as I said, I will first discuss the morphology of solidification structure, how it evolves, and then the types of ingot casting, and also I will discuss about the defects that are easily observed in the ingot casting. Now solidification morphology. Solidification morphology, as we understand, it means that is whether it is a planar solidification or cellular solidification, columnar dendritic or equiaxed dendritic. So this type of morphology of solidification structure can be mapped in a temperature gradient and solidification rate in a two-dimensional domain of thermal gradient and solidification rate. We can map all this morphology. Not only that, we can also map the scale of solidification substructure, that is what is the interdendritic spacing and all these things by what is the term that is called the G into R. That is the solidification at the temperature gradient into the rate, that is the solidification rate or the growth rate. If you take the product, it basically gives the cooling rate. Okay, so that GR basically gives the scale of solidification substructure. If the cooling rate, as we know, if it is lower, then it allows the diffusion significantly and the grain become coarser. What about the morphology? That become coarser. And if the cooling rate is fast, then the morphology become finer. Okay, and the morphology, you can predict the morphology by using the term what is called G by R, not GR. GR gives the cooling rate and G by R gives the idea about the morphology of the structure. As you can see, a very high G by R basically gives your planar solidification. That has to be very high value. And then if it is lower, then it will be transferred to place the cellular structure. Okay, and then you can have a columnar dendritic, then columns as well as some dendrites will also grow. That's why you can see there is a two-dimensional solidification. This is columns and these the dendrites are forming. And then you can have equiaxed dendritic structure. There is a very fine equiaxed structure you can get at a very low GYR value. Okay, and you can see, so these are the straight line you can see that demarcates the different GYR and the different regime of morphologies. Okay, and if you go in this direction, there is the cooling rate increases in this direction, and you can find that you can see the structure, all the structure become finer as you increase the cooling rate as you go in this direction. So it has become finer. This is the structure, this is the become finer. So thing is, okay, we can show it more. That is this is the lower cooling rate, and the cooling rate is increasing in this direction as you can find, and as a result you can find the structure is that is, you can see the cooling rate is increasing in this direction. As a result, you find the structure is coarse structure and is becoming a fine structure. Okay, and G by R is decreasing in this direction. That is, if you can see, that is G by R here, that is the G by R is decreasing. As the G by R decreasing, you can find the morphology become planar to cellular to columnar dendritic and finally equiaxed dendritic. Okay, so this is very so we can it is obvious that we can predict or we can estimate the what type of morphology is going to evolve depending on G by R or G into R. Okay, so based on that we can define what type of solidification structure we are going to get And so we can basically, the morphology and the solidification substructure can be mapped in a two-dimensional domain of thermal gradient and solidification rate. So thermal gradient, as you know, temperature gradient, that is Kelvin per second, and a Kelvin per centimeter, that is the temperature gradient, and R is unit as it is say centimeter per second, that is the solidification rate. And GR has a unit of Kelvin per G into R, solidification rate has a unit of Kelvin. So if we write, there is the R is basically, if you write it centimeter per second, and you can write it is Kelvin by centimeter, then cooling rate, that is the GR has a unit of Kelvin per second. Okay. So this is the thing. So then, so just now what I said, it is written here, there is the solidification morphology and scale of solidification structure can be mapped into two-dimensional space of temperature gradient and the solidification rate. G by R determines the morphology of solidification structure, and the morphology changes from planar to dendritic with decrease in G by R, as you can find, or decrease in thermal gradient. Obviously, if the thermal gradient decreases, or R increases, or the rate of solidification increases. And GR, basically the cooling rate, that is the cooling rate determines the scale of solidification structure, as I said, and the structure becomes finer with increase in GR as we move in this direction. So this is the gist of this. So based on basically temperature thermal modeling, you can calculate the temperature gradient as well as solidification rate at the solid liquid interface, and then you can predict what type of morphology you can get or what is the scale of solidification structure. Okay, now variation of G by R with the progress of solidification. As the solidification progress, then how the G by R evolve with time. This is the previous picture for your reference, I have just put it. So if you, what happens at the initial, when the solidification starts, suppose you have put a liquid metal in the mold and solidification starts, initially the thermal gradient is very high because mold at 30 degrees centigrade and the liquid is at temperature, pouring temperature, maybe liquid still maybe at 15-60 degrees centigrade like this. So huge temperature gradient is there. So initially you have a large temperature gradient and solidification rate is less at that time. So as a result, your G by R is a very large value, very large value. Okay, so initially, so that's why what happens, so you can get some dendritic structure, equiaxed fine dendritic structure, because G by then since G and R both are high, then GR, this the cooling rate is very high. Since the cooling rate is high, the solidification substructure is very fine, okay, very fine. So you can get, and initially the number of nucleation site is also very high at that time. So you get some equiaxed fine, equiaxed dendritic structure, equiaxed structure, fine equiaxed structure, you get it. But beyond that, what happens, your thermal gradient start decreasing. Why decreasing? Because as the solidification cell grow, then the temperature gradient is liquid temperature minus the solidus temperature at the solid, because the solidified shell, you can consider the temperature is the liquidus temperature, solidus temperature. So temperature gradient significantly decreases beyond that point. Or you can say the mold surface temperature also will go on increasing. If I consider the mold surface, that temperature also go on increasing, and also the liquid temperature, their liquid temperature go down decreasing. So as a result, the temperature gradient will decrease. Do you understand? Temperature gradient will decrease because the liquid temperature with time decrease and the mold surface temperature, because I will not take the solidified shell thickness, because thing is that you will have two resistance in series. One is in the liquid, one thermal resistance, another resistance in the solidified cell. So temperature gradient will lie from the liquid temperature to the mold surface temperature. Now mold surface temperature will increase little bit, but the liquid temperature will decrease significantly. With time, the liquid temperature, because heat is extracting towards the wall, from the liquid heat is going to the, it is going out to the atmosphere. So as a result, liquid temperature will go down. So as a result, your thermal gradient will decrease. And as the solidification progresses, I will show you, as the liquid fraction decreases and your solidification rate increases significantly. Okay. So R basically increases. Okay. So let us come to that point. Let's pace down. So during solidification, initial G is very high, that leads to very high G by R and high GR, basically promoting fine equiax dendritic structure, because here the nucleation site become very large. And since the solidification rate is very fast, so small nuclei grow to smaller extent, so a lot of fine equiax structure you get. And with further progress of solidification, G decreases because the liquid temperature decreases, and also the solid mole surface temperature increases, and the R start increasing with decrease in the liquid fraction. As the liquid fraction your decreases, R increases. I will show you from a heat balance, resulting in decrease in G by R that results in a columnar structure. So this is the heat balance. If you just make an heat balance in a massy zone, solid liquid massy zone, you can see from the solid the amount of heat that is coming in, that is the, you can say, calorie per second or energy per unit time that is in through the solid massy zone interface. That will be simply Ks, thermal conductivity of solids, into thermal gradient, that is the Fourier first law. This is the flux, that is the conductive flux, K into Gs. G basically the thermal gradient, dt dx. So K dx is the flux into A, that is the energy input per unit time. So this is the amount of energy that is input at the massy zone interface, and this is the amount of the heat that is going out to the liquid, that is simply A KL into GL, similar logic. So this much of heat is going out, this is going in. So if you just make an energy balance, this is the heat that is going in and going out, and say let us take that this much of heat transfer take place during time delta T. So this is the total amount of heat that is remaining inside it, okay, because this has come going down and this much of heat is there inside. So what it is doing basically, so rho L into FL A into delta R into latent heat of fission, this is basically the heat evolved. So whatever the heat that is coming from the solid to the massy zone plus the heat evolved during solidification should be equal to the heat that is going to the liquid. So that is the heat balance I have given, and this is the amount of solidification heat that evolved. So you can see that is A into delta R is basically the volume, delta R is the thickness that is getting solidified, into A, that is the volume that is getting solidified, into rho, basically mass that is getting solidified. Now, or you can say this is the volume that is getting solidified, into FL. FL is the liquid volume divided by the total volume. So basically FL A into delta R is the liquid volume that is getting solidified. That is because in the solid liquid massy zone you have solid as well as liquid. So this is the amount of the liquid that will get solidified, into density, that is the mass that will get solidified, into L, latent heat of fusion, that is the amount of heat that will be evolved. So this is the heat plus this heat that is being conducted into the massy zone, that should be equal to the heat that is going to the liquid. So this is the heat balance statement, and if you rearrange, you can write that is the rate, solidification rate is equal to delta R by delta T is this. So now here you can see interesting, that is the R depends very much inversely proportional to the fraction of liquid into the massy zone. So as the fraction of liquid, as FL tends to 0, R become increasingly high, infinitely high, very high. So you can see with the progress of solidification, as the massy zone, as the liquid decreases, so your rate of solidification increases significantly. So during the end of as the solidification progresses, basically liquid fraction decreases, as a result your solidification rate increases, okay. So that I am telling, with the progress G decreases and R increasing, as a result your G by R decreasing. With the progress of solidification, G by R decreasing. As the G by R decreasing, you are moving towards the columnar, to the columnar degree dendritic, there is the columnar structure. So after the skin that forms on the mold surface, and then a columnar zone grows, and the columnar zone grows. So you can see that is the form, we can write it from the skin, you have a very equiaxed skin is there, and then you develop this type of columnar grains that develops because G by R decreases, and finally when you go towards the center, okay, in that case your R become very fast, so your G by R become very low, so you again develop some right equiax dendritic structure. So along with it, because in case of the alloy solidification, along with it the constitutional supercooling also add to the undercooling, and that also promote this equiaxed structure. Anyway, but from this also you can understand that is as the G by R become very low, you will have equiaxed structure. So basically in this direction you can see G by R is decreasing. Okay, so also your G by R is also increasing. G by R decreasing means G is decreasing and R is increasing, like that. So you can get this type of structure. Okay, so at the end of solidification, R become high and the liquid fraction becomes tends to 0, leading to again very high equiaxed gradient in the structure. That is the thing that I said. So now I come to the ingot casting. Now you can see there are basically two types of castings are made. One is called the top pouring, by which you can pour the liquid steel just over the ingot. That is, the ingot casting means is a batch process. You pour the liquid steel into ingot and then allow to solidify and then take out the ingot. That is called ingot casting. Okay. So you can pour the liquid steel in two ways. One is just directly from the top like this, and then or one by one you can pour it, then pour it, then pour it, and then it is getting solidified. Or you can pour the liquid metal through a sprue and then you can feed it from the bottom. So it is called the bottom pouring or the bottom feeding. Okay. So in this case basically the atmospheric interaction is very high. In case of the top pouring, as you can understand, it interacts with the atmosphere and a lot of turbulence at the surface is there. So atmospheric contamination like oxygen and nitrogen can get into it, the steel become little, that is the inclusions are become more. And besides, since liquid is poured from the top, the last liquid to solidify is the top. So due to sinkage, it causes a lot of bigger cavity at the top. In case of the bottom pouring, those two problems are avoided. First of all, it is the liquid is poured, that is the feed from the bottom. As it is fed from the bottom, this surface remains tranquil, very tranquil, and so interaction with the atmosphere is not high. So steel will be much more cleaner. And second thing is that since it is not the last liquid to solidify is not here, it is fed from the bottom. So hot liquid is there at the bottom. So this is not the last liquid to solidify. As a result, you can have a less shrinkage cavity. So your yield is more in this case. So that thing, there is here basically a lot of atmospheric interaction, less yield. Here you have more clean steel and with a higher yield. And this is a large scale pick casting machine. You can find this is the large scale pick casting machine, that is ingot casting. So number of ingots are cast and then you can see the continuously ingots are getting formed here. So it is a endless pellets is there. You just pour the liquid into the pellets and then it gets, when it is moving, it gets solidified and then one by one ingots are casting. It is a large scale production of ingot. Okay. Now classification of ingot casting, basically two types of castings are there. One is called the kiln steel, another is called the reaming steel. What is the kiln steel? In case of the kiln steel, you basically the liquid steel that you pour into the mold, you completely deoxidize that steel. Okay, so you do not keep the, that is the, you kill the steel by aluminum such that the oxygen into the liquid steel is less than 1 ppm, very less amount of, very less. So completely deoxidized steel is cast in the ingot, that is called the kiln steel. In reaming steel, you do not kill the liquid steel completely before pouring. Okay, you partially kill it, you keep significant of oxygen into the bath such that during solidification that oxygen come out, react with the carbon, forming carbon monoxide bubbles, and that gives a stirring into the liquid steel during solidification. And the stirring has, as you know from segregation point of view, this stirring will help in reducing the segregation, because the more the liquid steel is stirred, the segregation will be less. And in case of the kiln steel, there is no gas evolution during solidification. As a result, you will have some macro segregation will be there. Okay. So, but there is a natural, very mild natural convection that carries the rejected solute in certain pattern. Okay. So, it yields the positive segregation, you will see. In case of the reaming steel, since the bath is significantly stirred, you do not get any macro segregation because it is mixed, liquid is throughout mixed. So, composition is homogenized all the time. but here it is not. Since gas evolution is not there in case of the kiln casting, the composition is not homogenized. At the solid liquid interface, the impurity reaches, and this impurity rich region may be carried by the mild natural convection, and then they can in a different patterns they are collected into the structure in the casting, and that give rise to positive segregation. So this is the two things. First thing, that is the idea. Basically, one is totally killed and partially killed is that to give some kind of studding, that is called the rimming steel. Why it is called rimming steel? Because it generates some kinds of rims. You can see that is the rims. This is the that is the rimming steel. You can see the blowholes. This is the this is the skin, and then this is the blowholes you can find, primary blowholes, and this is the secondary blowholes, and they form in the form of rings. That's why they are called the rimming steel. Okay. Now, casting in the kiln steel is usually cast in a wide end of mold. Wide end of mold means this type of mold is there. This is called the wide end of mold, that you cast it right in wide end of mold. If you cast this way, then basically in case of the that is the this thing, that is your rejection will be less because sinkage cavity is less. But if you cast it in a narrow end of mold, then you will have a lot of sinkage, so your cut will be more. So this is the narrow end of mold, and if you cut the kiln steel in a narrow end of mold, then your sinkage cavity is much deeper. And if you cast a kiln steel in a narrow end of mold, then your sinkage cavity is less. Okay, as you can find. So as a result, yield will be better. So cast in a wide end of mold, and it is cast in a narrow end of mold, but rimming steel is cast in a narrow end of mold because in case of the rimming steel, this type of sinkage doesn't happen because the liquid is homogenized all the times, both chemical compositionally as well as thermally. So temperature is everywhere in the liquid more or less same. So solidification take place all throughout all directions. Okay. So shrinkage cavity is usually less because last liquid to solidify here also it is get started. So shrinkage cavity is much less in case of the rimming steel. That is also another idea. There is a rimming steel. If you start the bath, your shrinkage cavity significantly become less. You can find only small shrinkage cavities there. So it is, if it is cast in a narrow end of mold, it is better than the gas pressure that develops. It will have a little better pressure, a little higher pressure. Gas pressure will be little high. The starting will be more vigorous. If you cast in a wide end of mold rimming steel, then the gas will easily escape to the atmosphere, so it may not give that much of vigorous starting. Okay, so just like this. So cast in a narrow end of mold in case of rimming steel, and kiln steel cast in a wide end of mold. Yield loss due to piping, that is the kiln steel is well known for the yield loss, a lot of shrinkage cavity. That's why yield is less. Kiln steel, rimming steel yield is much higher. Okay. No blowholes and good surface finish. In case of the kiln steel, you don't get any blowholes. So surface finish, here you can see after the skin lot of blowholes are there. So if you want to forge the rimming steel, it will be difficult. Then this, because these pores will be opened up, and as the pores opened up, that will form the scale and the defects. So but in case of the, you can see in case of kiln steel, the surface is very smooth. I will show you later on. Although it has a macro segregation inside, but the surface is very smooth. So kiln steel are good for forging because they don't have blowholes on the surface, so it is good for forging, but they form the blowholes in the forms of rings and near the surface, so they are not good for forging, but they are good for flat products. That is, the rimming steel is good for the flat product because these pores can be welded, because since you are reducing the thickness, they can be welded, and they will remain inside, and they will not be exposed outside. They will remain inside and the welded. So for flat product is perfectly okay, but if you want to forge a product, then it should be a kiln ingot. And the macro segregation problem in the kiln steel, the macro segregation is a problem, and macro segregation is less in rimming steel. So rimming steel is aware of, that is the defect. They don't have much less defect is there. They can avoid the defect. Macro segregation is less, macro segregation is more. I will show you just how does the kiln steel look like. This is your kiln steel. You can find a very fine skin is there, and this is the columnar grains and like this. So you don't have any blowholes here. Okay, don't have blowholes. Then equiax structure is there. Fine equiax structure has formed, and inside throughout equiax structure. And then you can find these are called the positive segregation. This is called the A type segregation like this. This is the C type segregation. All are positive segregation. And this type of pattern basically form because of very mild natural convection that take place into this structure. Okay, so this is positive. And you can see there is some negative segregation. Basically the liquid, there is the solid particle, that is the solute-less depleted, that is the particle gets deposited here because they become heavy, that is the after the solidification. So that's why that is the, I'll just come to that thing. So this is a negative segregation. And the large macro segregation in absence of forced convection, as I said, and macro segregation is a defect that cannot be eliminated by annealing, that I have said. So these are really defects. And mild natural convection places the solute and is liquid in the form of A and C type positive segregation. And impurity depleted heavy liquid, basically when the impurity depleted, first liquid to solidify is basically your impurity depleted. Okay, so those become heavy, they try to settle at the bottom, and at the end basically the liquid, as you progress the solidification, the liquid become richer and richer in impurity, so they become lighter. So that's why the positive segregation in the upper part. In the lower part, basically first liquid to solidify are much less in the impurity. Okay, they are and they become heavy and then settle at the top, and the impure liquid basically they are lighter and they form the positive segregation in the upper part. And this pattern, as I said, by the natural convection. And as I said, the solidification morphology it follows. There is the skin is fine equiax, then the columnar, then again equiax like this. Okay, so this is about your morphology and segregation of the kiln steel ingot. Okay. So you can consult the book of Ghosh and Chatterjee. As I said, this ingot casting is not very much in use today, and mainly in some plants they are basically ingots are used for forging purpose, and that is fully kiln steel, and the flat product are basically produced from the, that is mainly continuous cast product basically used for the making the flat product today. Okay, so the conclusion we can say is the solidification morphology and the scale of solidification structure can be mapped into two-dimensional domain of thermal gradient and the solidification rate. And the morphology of solidification structure can be determined by G by R, where the GR, that is the cooling rate, will give you the scale of solidification substructure. And with decrease in G by R, the structure changes from planar to columnar to dendritic. And with progress of solidification, G by R decreases. As a result, you can, from the surface towards the center, the structure changes from planar to columnar to dendritic. During solidification, initially G is very high, that leads to a very high G by R. And as I said, and promote the equiax structure or the planar solidification to some extent you can say. And then with further progress of solidification, G decreases and R starts increasing, and that basically decreases the G by R. So two types of ingots are usually cast. One is called the kiln steel, which is produced from the fully deoxidized steel, and the deoxidized steel. And this kiln steel has major problem is that yield is less because of lot of shrinkage cavity forms, but no gas generation take place. As a result, the skin become very fine. There is no blowholes are there, so it is very suitable for forging product. And semi-kiln steel are basically used for making the flat products. Okay, because they do not have much of segregation, and that is the very important thing. And they have some blowholes, but they can be easily welded when you roll them. So, okay, so they are very good for the flat product. But today, as I said, the ribbing steel is not cast too much because most of the flat product are produced by continuous casting, and that is also fully kiln steel, and the continuous casting you can produce the flat product. And in some industry, that is your kiln steel are made only to produce the forging products. Okay, thank you very much.